NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How are we all tonight? Everybody good? Cool. Well, thanks for coming out to join us, as always. So let's hop right in, shall we? Earth science is a key to understanding our universe. After all, planetary science relies on ideas and technologies developed and tested here on Earth. Like a Star Trek sensor sweep, a remote sensing technique called spectral mapping is used to learn about celestial bodies. These types of instruments use reflected sunlight to produce imagery of the chemical composition of planetary surfaces, and the information captured by these instruments is useful to many fields of Earth and planetary research. In this talk, our guest will share photos and videos of various spectral mapping field deployments and will discuss the science behind measuring spectra of reflected sunlight and perform physical demonstrations to illuminate a few of the phenomenon that make spectral remote sensing possible. Tonight's guest received a BS in physics from the California State Polytechnic University, Pomona in 1991. From 1991 to 2005, he was the calibration and validation field engineer for the multi-angle imaging spectroradiometer here at JPL. From 2005 to 2011, he was employed by Northrop Grumman Aerospace Systems as an electro-optical calibration engineer. He has also worked with LabSphere Incorporated, a maker of optical calibration systems, as their worldwide remote sensing systems development and marketing manager. During these gap years, he was brought in part-time by various JPL projects to help out with ongoing fieldwork. He returned full-time to JPL in 2012 to augment JPL's imaging spectroscopy group. There he helps calibrate, operate, and develop custom spectral remote sensing instruments and techniques for NASA and other customers, as well as assist with planetary research and exploration development efforts right here at JPL. Ladies and gentlemen, please help me welcome tonight's guest, Mr. Mark Helmlinger.
Very good. I thought that sounded good. Thank you, everyone. I'm honored to have been asked to speak this evening. I'm part of a large dynamic team, and you all know who you are. I'm just one of the minions of JPL's imaging spectroscopy group. This Von Karman lecture is about the science, application, and pursuit of imaging spectroscopy. I took this snapshot while flying aboard a research aircraft, dodging storms in transit to our next experiment. More on the pursuit of imaging spectroscopy later in this talk. First, let's put imaging spectroscopy in context. JPL studies planets, including the most important planet in the universe, our Earth. It's sort of an inside joke here at JPL when a focused researcher has to be reminded of our place in the universe. To JPL, Earth is one of a growing number of evolving planets, but so far the only oasis and example of life. Imaging spectroscopy is a powerful tool for studying planets. White, gray, yellow, blue, green, or red, imaging spectroscopy lays bare the chemical composition of a planetary surface. From the static climate of Mars to the rapidly changing climate of Earth, imaging spectroscopy measures and maps the environment. Planets are best understood in context, and Earth is the planet we know best. One of the things that is studied at JPL is comparative planetology. That's an evolutionary understanding of planets, which makes plain a couple of cosmic examples in our nearby heavens of rocky planets that started out with similar environmental inventories as we have here on Earth, but are now lethal. Venus is a planet that could have been a sister of Earth, but for a runaway greenhouse effect. Mars, runaway greenhouse effect that can melt lead on the surface. Mars is a planet with a surface blasted sterile by our sun's ultraviolet emissions because of no protective ozone layer. And we know these things through the application of remote sensing techniques, including imaging spectroscopy. So if we look at this infographic, it documents JPL's mission history, where we've gone up at the top, or in the middle where all the planets and bodies are, and then on the bottom when. You really can't see it, but those are all dates down there, right? And you can tell by all the green lines going to the green planet that JPL's been to Earth often. And there's a deep and productive synergy between Earth science and planetary science. Extra points for those who noticed that this infographic does not include the New Horizons flyby of Pluto. Yeah, where's Pluto? It didn't get demoted. This infographic was made before New Horizons went by. So spacecraft flying by, or orbiting, or a rover, the point is to figure out what's over there without going over there. That's what remote sensing is. So imaging spectroscopy is a scientific remote sensing tool. And remote sensing is something NASA does best. All of America's government agencies, only NASA has the critical concentration of brains, experience, and know-how to get up there, get out there, and make the measurements of whole planets. JPL is managed by Caltech for NASA, which has given JPL the mandate of robotic extraterrestrial exploration. The group I work for has been a key part of many of those extraterrestrial missions. Galileo, Cassini, the Mars Reconnaissance Orbiter, even the Indian lunar Chandrayaan-1 mission there has been a spectral imaging system on nearly every major planetary probe built or operated by JPL. And the people of the imaging spectroscopy effort at JPL, where I work, have built or been involved with just about every one of those imaging spectroscopy instruments. And it's been a steep learning curve for me ever since I walked through that door. Even Curiosity uses remote sensing, even though it's on the surface, to make a decision about traveling to a potential site and collecting a sample to analyze with their onboard chemistry set. For many remote sensing measurements, in nearly all of the memorable images over the history of planetary exploration, the amount of reflected sunlight has been the quantity measured. For that fraction or pixel of the scene, and that fraction of the solar spectrum or wavelength, the number returned to the Earth, to us here on Earth, is the amount of reflected sunlight making it back to NASA's sensor. As part of my career, I've been sent to the corners of the Earth to help calibrate instruments in the A-train orbit, depicted here in the lower left. Those instruments use reflected sunlight. Many of those instruments use reflected sunlight. Constellations of Earth-observing satellites are some of the most powerful tools of science for accurately measuring the ever-changing environment of our planet. The A-train, or afternoon train, of Earth-observing satellites is in a special precessing polar orbit called sun-synchronous that enables not only planetary coverage, but consistent, repeatable Earth observation at the same angles of solar illumination for every orbit. That's how carefully these measurements are made. When it has to work for everyone, everywhere, every time, no matter what, science is used. And at NASA, it's our job to make it work. I have to put the cursor there and then do this. This talk is about a remote sensing technique called imaging spectroscopy. It is a measurement strategy that identifies surface materials and their physical context lying next to each other, right? So down in the lower left-hand corner, this is a data cube, a way of representing imaging spectrometer data. The top of the cube is made of data from wavelengths of light that our eyes perceive as the colors red, green, and blue. Imagine that you could automatically discern what material predominates in each pixel of this image. Dirt, vegetation, asphalt, concrete, roofing, automatically classified, mapped, counted, and more. How those materials interact with sunlight is represented in the third dimension of the cube, those colors going back. It's the spectral signature of reflected sunlight. And it's by this signature that we know what's down there. This all happens within the context of the electromagnetic spectrum represented up at the top there. And that's measured by wavelength. And we perceive wavelengths of different amounts of electromagnetic radiation as color. But we only really see in 3 spectral bands. And that's what is represented down below the plot above where it says wavelength nanometers. Those are the 3 spectral bands that the cones of our eyes are sensitive to. Our brain interpolates the rest of the colors of the rainbow from the relative intensity of those 3 bands. So I'm going to do a demonstration next. But before we get there, this image over on the right, this RGB image, it's more than just a pretty picture. It's actually a scientific image of physical reality. And extra points, you may have noticed, Who can tell me why the shadows are blue? Anybody want to try?
They're illuminated by the blue glow of the sky.
That's right. Shadows are not illuminated by the white light of the sun. They're illuminated by the blue sky. But our eye does a lot of automatic white balancing that we're just not aware of. So here we have an example of seeing is not believing. Our senses are limited, and there's more to the universe than we can sense. And so I'm going to do a demonstration, my next slide, to show that. So I have here something called an integrating sphere. I use these professionally. They present a uniform field to the eye or to a camera. Every cell phone camera or professional camera ever made has stared at one of these things on the production line and had its relative responsivity field measured. So what this integrating sphere does, by the way, integration is a fancy mathematical term for mushing up. This has got some light bulbs inside of it, and it's mushing up the light, and so much that you really can't discern much. See, this is actually an empty sphere that's painted white on the inside. I don't have a film over it, right? And this is a cake mold from Michael's. You can, it's exactly the volume of one box of cake mix. It comes in 2 halves. You make the 2 halves, you bake them, glue them together, and you got your soccer ball cake. My good wife Susan turned me on to this thing. It's great. So yeah, I make these for teachers. And what it's got illuminating in it are 3 LEDs. So you see pretty much here a white light, right? But if we look inside, we can see that there's really 3 light-emitting diodes in there that are the 3 colors that our eyes are sensitive to: red, green, and blue. And maybe if I walk around a little bit, you can see it's just red, green, and blue inside. There's no white light bulb inside. So let me really freak everybody out. What color is this? Really pretty yellow, isn't it? Right? Very pretty yellow. But if we look and see what lights are on inside, all I did is I turned off the blue light, and it's the red and the green that's on. So if there's a wiseacre in the back of the room giving me trouble, I'll say something like, okay, Einstein, where's the yellow light bulb? Got to be a yellow light bulb in there somewhere, right? No. Yellow is the color in between red and green in the rainbow. Your brain knows this. It's hardwired into your eyes, actually, into your optic nerve. And so you see yellow. So the word magician means I'm going to fool you. I've explained how I'm going to fool you, and I'm still fooling you. It's built in. Magicians know how we're built inside. But this is an example of subjective versus objective. Objectively, I've explained a way of looking at the universe, but subjectively, you say, that's a yellow light. That's not a red and a green light. And if you take a magnifying glass, by the way, I can get all kinds of other colors. I don't know if I can get all kinds of other colors just by changing the, switching things on and off and changing the relative intensity. That doesn't show up quite so well. And I can get magenta, I can get yellow, and cyan. So those are the intermediate colors. So if you take a magnifying glass to any cell phone screen, television screen, computer screen, you'll see it's made of little dots, pixels, and they're all red, green, and blue. And by the various intensities, they fool you into seeing all the colors of the rainbow. So science is about physical reality, and much of the real world is beyond human perception and intuition. And science really is the best survival tool ever devised by humankind. And spectroscopy is a historically significant and powerful analytical method that enables remote measurement for scientific discovery and other applications. The tools and ideas of spectroscopy are deeply woven into the development of the scientific method. And that's why I say that imaging spectroscopy is a scientific remote sensing tool. Newton, Fraunhofer, Bunsen, Kirchhoff, Hubble, these are only some of the giants upon whose shoulders we stand. Measurements made with spectroscopy indeed show that the laws of physics are universal. The furthest stars have the same elemental spectral fingerprints that we can generate and measure for ourselves here on Earth, thereby showing the laws of physics apply everywhere. So please, at this time, allow me to introduce my associate, Andrew Thorpe. He's a methane hunter. In the upper left, he's surveying a river near Mangalore, India. In the lower left of the slide, he's with the Avarice Next Generation Instrument and a King Air research aircraft during our recent campaign to India. In the upper right, he's carefully measuring upwelling spectral radiance from a known reflectance target at Ivanpah, California, which is a playa, or dry lake bed, many of you have driven across on the way to Vegas. It's right on the state line. The imaging spectroscopy group at JPL uses it as an in-flight calibration target. In the lower right, here's Andrew at JPL's open house, and in the center, Andrew is measuring methane emissions from 16,000 feet. So now we're going to do another demonstration about light and about science and skepticism. So you may have heard that Sir Isaac Newton, one of the giants upon whose shoulders we stand, used prisms to make rainbows, and he had an extraordinary claim. And that claim was that, well, let me turn this on. But this is, by the way, kids, this is an overhead projector, if you've never seen one before. It really was a surprise for me. I go to a lecture at a classroom and they go, what is that? An overhead projector? What do you want? So what I'm doing is I'm using it to project a slit image, which we have here on the card that Andrew's holding. White light. So Sir Isaac Newton took a prism. By the way, I think it was Fraunhofer made his living by making glass clear enough and pure enough to make prisms and lenses out of. It was actually a German state secret for a while. And Newton put this thing into the light and he dispersed it. It's called dispersion. And he made all the colors of the rainbow. And his extraordinary claim was that the white light was made of the colors of the rainbow. Now, extraordinary claims demand extraordinary proof. And making that claim just wasn't enough for the truly skeptical. Now, skepticism is part of science. There's a difference between skepticism and cynicism. The skeptic can be convinced with the correct evidence and a good argument. A cynic can never be convinced. In our common language, we often confuse the two terms, but there is a distinction. So the truly skeptical will say, well, the colors could be coming from the glass somehow. And Newton said, aha, but if I recombine those colors, so I'm going to put this other prism in the path of, if I get it right, Andrew, don't move. I always mess this part up because it's counterintuitive. No, that's doubling. Oh, this way. There we go. So what I've done is all the colors are hitting this second prism and they're getting recombined, and you can see the moving. There we go. So the bright slit on the left of this card is the recombined light that's gone through the two prisms. The dimmer slit is what we call stray light, but it's illustrative of where the light would be falling had it only gone through no prisms, as a matter of fact. So there's a little bit of an offset, kind of like in a pair of binoculars, because of the two prisms. So that kind of circularity, that reversibleness of a physical principle is an important part of demonstrating to a skeptical audience, when you write your paper, your peer review, everything almost like that, how the mechanism works. And a truly, in the consistent demonstration of mechanism, how it works, okay? That's what sets science apart from opinion. And which is just a fancy way of saying that science is about finding what's physically true for everyone, everywhere, at all times, no matter what. Okay. I should probably turn this on, Andrew. So like I said, when it has to work, NASA uses science, right? We make it work. Imaging spectroscopy uses spectral fingerprints from reflected sunlight to detect, identify, quantify, and monitor surface chemistry, its physical structures, and dynamics. On Earth, its uses encompass a breathtaking range of applications involving science, the environment, resource management, and economics. This slide documents the flow of information from collection to processing to product. Now, note, for expediency, not all of the data products nor photos I am using are rigorously attributed. Suffice to say, they represent the evidence of efforts of thousands of dedicated and hardworking folks who use imaging spectroscopy to answer questions about our world, other planets, and the universe. So one of our imaging spectrometers, actually two of them now, fly sometimes aboard the ER-2, which is a high-altitude research aircraft. It's a jet-powered glider, flies at 65,000 feet, 20 kilometers, twice as high as commercial jetliners. The great thing about flying in the ER-2, even though it's at the top of the atmosphere, it's almost like being in space, but unlike space, we get the instrument back when we're done. And the way the instrument works, it has several elements. You can see the word telescope, slit, spectrometer, and detector array on there. Well, that gray line on the ground gets scanned by the forward motion of the airplane over the ground, kind of like a scanner, a platen scanner scans a document. And that light is then focused by the telescope onto a slit, very similar to the slit I have set up in function on the overhead projector. Goes into a spectrometer, which is a way of dispersing the light like what the prisms do. And that goes onto what's called a detector array or a focal plane array. One dimension sees all the differences in the brightness as it goes along and builds the picture up. And in the other dimension on the focal plane array, it sees the spectral signatures. And so that's kind of like, because the focal plane arrays that we're using for the instruments in the ER-2 are 640 by 480 pixels, we can see 480 different wavelengths and 640 lines on the ground, or it's like we have hundreds of parallel spectrometers, and that's why it says that. And each one of those spectrometers then assigns a spectral signature to each pixel in the data block. That's what the calibrated image cube in the middle is all about, and then over on the right, from that we can use our understanding of physics and how sunlight interacts and reflects off of different chemical materials to make a material map. Now the difference between a pretty picture and a scientific image is actually the little key over on the right in the white. Is what all the colors mean, and that's how we learn about the relative positions of things and the relationships to each other. And if you fly the same target many times, you learn about the dynamics, how it changes with time. So this is an example of a geological data product made from imaging spectrometry data actually wrapped onto a digital elevation map. So in the background, the hills are colored, rendered in natural colors. Rendered meaning the data is turned into red, green, and blue channels that your eye can interpret. False color imaging, controlling those red, green, and blue channels of the display with other kinds of information, it's often used to visualize data. The colors in this case are keyed to the surface expression of mineral type, and the placement of minerals that are otherwise invisible to the eye is shown. So more than a pretty picture, the mineral key at the bottom and the positions on the map enable a geologist to read the local story of a dynamic Earth. This is a story that can help locate economically exploitable resources with the confidence needed to justify large-scale investment, in this case, where the gold is. So mineral extraction can bring toxic materials to the surface and concentrate them, and knowing what is happening and where can be used for exploitation choices with a lower overall cost. Here, airborne imaging spectroscopy has been used to identify and map Superfund hazards for the EPA at Leadville, Colorado. This is another example of airborne imaging spectroscopy. It can be used to map vegetation species, and this is Santa Barbara, California. Now, some species are invasive, some are dying out, some are drying out, others are on the move year after year in response to our changing climate, and all can impact property value. For example, if you wanted to buy a piece of land in Santa Barbara where there's a lot of California live oak, you'd look for one of the redder parts of that plot in the lower right corner. For industrial agriculture, spectral mapping assists with crop optimization and cost management, irrigation and fertilizer application, as well as optimized crops rotations to match climatic trends are some of the applications enabled by imaging spectroscopy. Now, mixed species forest management helps preserve historic environmental conditions. It also helps the tourism industry. And a careful accounting of current and evolving conditions is essential to effective and economic resource management. And so you can see the very, very detailed map of speciation. And these speciation maps will change with time. It'll be very interesting. I've talked to those guys. They make it sound really interesting. Avarice and other spectral imaging applications, fire science, perhaps of a little more interest to us locally. This is data from the Simi Valley fire in 2003. And here we have a thermal estimate product way on the right. And I'll show you how that works in a bit. And data like this can answer the question of how hot did the fire burn and where. So this is before the fire, some spectral imaging in the Santa Barbara area. And so we've got species type, dry biomass, and canopy water. That can all be condensed into risk assessment, fire prevention plans, and preparation. And this is the sort of on-the-ground knowledge that local government and the insurance industry have a stake in. Where's it going to burn the worst? Where's it more likely to really get going? And then once it does get going, here it is. Here's the Simi Valley fire. We were actually mapping flame front progress and temperature. And that can give you an immediate assessment of the severity and the damage that it's occurring and the likely recovery timetable and the likelihood of all kinds of consequences. Now, in the upper left corner is a plot. As an object gets warmer and warmer, it gives off more and more of different wavelengths of light. It's called Planck emissions or black body emission. If it gets hot enough, it actually starts glowing. And the different wavelengths that are represented, see each layer in the data cube of a spectral imaging instrument is actually can be displayed as a black and white picture. And each one of these slices is from progressively longer and longer wavelengths. And some of those wavelengths are affected by gases in the atmosphere and aren't useful, but others will go up to just a certain maximum, and that's as far as they go, represented by that green line. And if you can fit that green line to those areas that are more likely to get to that maximum, you start matching what's called the Planck curve of emission, which is directly proportional to the temperature. And so that's how they back out the burn temperature for particular pixels. In this case, way over on the right where the arrow is pointing, got pretty hot, as you can see. And then after the fire, spectral imaging spectroscopy can be used to prepare for the next season. You can do differential mapping before, after, and plan for recovery and, of course, develop future management scenarios and actuarial databases. So imaging spectroscopy can be used for shallow water spectroscopy, the mapping of water quality and bottom composition, and corals. The overall environmental quality and ability to support fishery populations can be mapped out and planned upon. Coral beds are the rainforests of the sea, and because they have tremendous biological activity and diversity. The Coral Reef Airborne Library, or CORAL program, has just come back from measuring coral reefs in Australia and the Southern Pacific, and is about to depart. In fact, my colleagues are in planes right now for Hawaii, Guam, and Palau. And the CORAL program uses an imaging spectrometer called PRISM, the Portable Remote Imaging Spectrometer. Here at JPL, we get extra points for making acronyms that make sense, which has been designed for aquatic spectral mapping in particular. Another application of this technology has been the Airborne Visible Infrared Imaging Spectrometer. Ooh, Andrew, I brought stickers. I forgot, they're in my backpack. Everybody will put them out in the back. The Avarice program has its own stickers, its own logo and everything. So, and we're JPL's premier imaging spectrometer, and that imaging spectrometer took this data of a red tide bloom in Monterey Bay. And red tides are toxic. They can negatively impact fisheries, shellfish beds and lobsters, tourism, etc. So here's another application. In April 2010, Avarice was used by a USGS, NOAA, and NASA science team to estimate the thickness and volume of the surface oil spilled by the Deepwater Horizon platform. In the upper left corner is imagery from the bottom and the top of the ocean. And we have an explanation of how the spectra were used in the estimate. There's an aerial photo in the middle bottom of what it looked like to the eye. And then this is over on the right, and also in this slide over on the left, the RGB bands from the Avarice data. But then we're able to use that spectral information. In the middle block there, we have something called the aerial fraction, and that's the fraction of the surface covered by oil. And then in the last block, big block, we have an estimate of the thickness of the oil. Those two could be put together to estimate the quantitative volume. And that's what that list is. You can't read the writing, but it's just a list of numbers. And that can automatically put into a computer all totaled up and to see how much oil was actually spilled. AVERIS has been used by a broad government and university science team since the spill to map vegetation species and physiological health of the Gulf before and after. These images and data are before and after. So before along the top, and ongoing monitoring, and after on the bottom, and then an oil impact product that can be useful to various agencies. This is an example of science being used to count the cost of the consequences of technology. Now, imaging spectroscopy is also used to study snow and ice. Here, our colleague Tom Painter, way at the top there, T. Painter, JPL, has flown an imaging spectrometer along with a LiDAR over snowfields, and he's found that how dusty the snow is can make the snow melt a whole lot sooner. So over on the left in the middle picture is dusty snow with a little white plaque on it. And that little white plaque is a material called spectralon. It's actually scientifically white. It's 100% reflective over a broad range of wavelengths. And you'd think snow would be as white as that stuff, but not always. And imaging spectroscopy can measure just how not white it is and make an estimate of how quickly it'll melt. And that's important because water availability and storage is what happens with snow in the West, and timing is everything, especially for the American West and the Colorado River. One of the issues the California water system is facing right now is warmer storm systems that drop more rain than snow on the Sierra Nevada, which is our great reservoir. Dr. Painter's program is called the Airborne Snow Observatory, or ASO. NASA JPL, in partnership with the California Department of Water Resources, has developed ASO. It's an imaging spectrometer and scanning LiDAR system which quantifies snow water equivalent amounts and snow albedo being how bright it is or how not bright it is. It is used to generate unprecedented knowledge of snow properties for cutting-edge cryospheric science and provide complete, robust inputs to water management models and systems of the future. So another remote sensing product that can be gotten out of imaging spectroscopy data is the 3 phases of water. And we've got the raw data on the left, and on the right is the data product where water vapor is signified by blue, liquid water by green, and ice by red. Now we've seen how red and green together can make yellow. So we've got ice and liquid water together just off the top of the volcanic. This is Mount Rainier. And so there's snow at the top. And this, again, can be put into a computer to estimate how much is there, how much there's going to be there when it all melts, maybe how quickly it'll melt. And volcanic ash on a volcano slope with too much water spells disaster. So it's a good way to map that. So this slide is an example of how an imaging spectrometer sees water vapor in the air. This was taken by AVERIS over Rogers Dry Lake, California. Note that the collects here are 15 minutes apart. Water vapor concentration in our atmosphere changes quickly and invisibly. It was a clear day to anyone standing there. A balanced amount of atmospheric water vapor is an important part of a planet that is alive. Water vapor drives the greenhouse effect, which keeps the Earth a little warmer than it would otherwise be at its distance from the sun. Someday soon, and I think that day has come if I just saw an article about it, when NASA looks for other Earth-like planets with special spectrometers that can pick them out against the overwhelming light of the star they orbit, the spectral fingerprint of water vapor will be particularly watched for. And I think a British team just found that in the atmosphere of a 1.4 Earth mass equivalent planet that occulted its parent star. And so in the occultation, they're able to see the light that's gone through the atmosphere and tease out the spectral fingerprint that says water, and I think they found methane there too. It just happened today. AVERIS has also responded to other national emergencies. This is the emergency response 5 days after 9/11. And the questions we were trying to answer with that data was, where did all the dust go? What was the nature of the dust? What was it made out of? How big was it? How bad was it? And where are the hot spots in the wreckage? Again, using that temperature profile technique that we were using for the fires. And that's 5 days after. There's still hot spots you can see down in the lower right-hand corner. And here I am on the Gulf Coast, during the BP oil spill. Note there's a field spectrometer on my back. No, it's not a Ghostbusters machine. And it's the same field spectrometer we have over there on the table, and we'll do some demonstrations with. And note, these are reflectance spectra, these squiggly lines. And we have wet sand, which is the blue line, dry sand, which is the white line, plants, the green line, and the yellow line, that's actually the parking lot that's just out of the picture. It's pretty dark, right? Parking lot's kind of a low number, dark. By the way, those two big bumps at 1418 something nanometers, that's where there's actually no sunlight and the signal to noise ratio of the instrument is rather high, and so you kind of get nonsense. And usually you blank it out, but I was too lazy with Excel to do that, and so it just comes out kind of looking crazy. So don't look behind the curtain, ignore that man behind the curtain, don't look at that part. But actually, if you could only see in those colors, those wavelengths of light, the Earth would be dark all the time because the water vapor in the air has absorbed all of that sunlight. At some wavelengths, our planet just looks like a giant white cotton ball. From the top and on the bottom, it's totally dark, even during the middle of the day. So if you look at the green line, if you look at the bottom, we've got 350, 500, 650. Well, 550 nanometers, because that's the wavelength in nanometers, and the bottom is what we perceive as green light. And look at that, there's a bump. What do you know? Plants are green. Yay. They're green because they use blue light and red light to turn sunlight and air and water into plant food. And they don't use red light that's redder than red or infrared, and that's kind of like plant sunblock, and so they reflect it more, a lot more. That big, tall, sharp, that's called the red edge, that's indicative of plants. If we ever see a spectra like that from another planet, woohoo, it's photosynthetic life. And those are what we call spectral signatures. They're a list of numbers that can be used automatically by a computer to identify the chemistry of the target. So now I'm going to make a spectrometer with Andrew's help out of that archaic overhead projector and these two prisms. Now you saw how Sir Isaac Newton dispersed the light with this one prism. Well, I'm going to disperse it even more with a second prism. Oh, there we go. Oh, that doesn't look so good. There we go, that's better. Okay, now I'm going to come around here. So what I have here are two business cards. Business cards are a great way to find light. If you've ever worked with optics, you just wave your business card around until you find it. And what this device is a solar cell taped in the bottom of the box, and this slit here allows the light coming, the rainbow of light coming through the slit to go to an amplifier and a display here, these LEDs going up and down. So this function here, moving back and forth like this, is what a spectrometer does. It either moves the prism or the dispersion element, or it moves the detector, or it has a bunch of detectors. That's what our in-flight instruments have. So that for each position here at the focal point, you can get a number, a list of numbers, and that's your spectral fingerprint. Now, I said there's more to reality than meets the eye, right? So here I can put the spectrometer where there's, where there's no light, and then I can put it where there is light. And you can see there's light entering. If I rotate it a little bit more, you can see it. So no light, and then there is light, and then no light, and there is light, and there's red light going into that slit. Agreed? Now, if we go right over here, there's no light going into that slit. Oh, but wait a minute, the scale's going up and down. In fact, this system's more sensitive to the light that actually is here, which is near infrared light, which we cannot see with our eye. There's a whole universe out there you can't see, beyond your human senses. And that's where a lot of the chemical fingerprints are. And then finally, the responsivity of the silicon solar cell goes away at about 1 micron. So we're looking at about 0.4 microns out here in the blue to about 1 micron where it finally stops. Okay? Give you an idea of measurement versus wavelength. And that is a spectrometer. A spectrometer measures the position of the focused light after it's been dispersed. So it's really like taking a tape measure, and that's how we measure wavelength. Time for another demo. I needed to come and push the button. So I promised you a Ghostbusters backpack. No, an imaging spectrometer. No, wait a minute. This is a single point spectrometer. An imaging spectrometer is like 600 of these things looking at the ground at the same time, like that. This is just one. And what we've got set up here, what Andrew has set up here, I'm going to rest my weary feet, is a spectral on plaque. The light that's coming from our source is reflecting off that plaque, and it's going into the pistol thing there. That's a sophisticated device that we call the gazinta end, where the light goes into. And it gets piped in a fiber optic, which is in that armored cable that goes to the body of the spectrometer, which has moving parts. And if you stick your ear to it and your heart is pure, you can hear it going zinga, zinga, zinga. And it's measuring the position versus time, which it interprets into wavelength versus intensity. And that's what's displayed up here on the screen. Now, what I've done, or what Andrew has done, is he's taken a reading of whatever that intensity is and made that a reference reading, and then he's dividing every subsequent reading. You can see here this little bar graph display. Every time that completes, it's completed a scan. So we took one of those scans, and now we're dividing every other one that comes along later on by that one that we saved. And mathematically, what do you get when you divide the same thing by the same thing? You always get the number 1, right? So that's what we see the line is at, number 1. And this is a testament, a demonstration of the stability of the system. The system is the source, and the system is the measuring instrument. And we have over on the left here the reflectance, the percentage of the light from 0 to 100%, or from 0 to 1, okay? So if we were to substitute that white reference plaque that we know is scientifically 100% reflective with a material, a mystery material, and we compare this spectral signature to what's here on the screen, what do you think? Never mind the letters on the, that's how I keep track of everything. These are white powders we're putting under here that look totally white and would be undiscernible without sticking your finger in it, tasting it, which I don't recommend for a couple of them. And so this is how a computer would recognize the chemical signature. So what do you think that is we're looking at there? What does that look like? Yep. Flour. Okay, let's try something else. So this one's a little different. Yeah.
Yep, sweetener.
Sweetener, the yellow stuff. Now this one's kind of fun because only sugar has this little hook here, this little feature, and this is due to a very specific vibrational state of the molecule. And in fact, that's people get their PhDs in figuring out exactly what this came from and why and everything else. Don't get him started. Anyway. Now plaster is interesting because plaster is actually gypsum. And gypsum is a mineral of interest here at JPL because so far the only way we know gypsum is made is by planets, is with oceans. And we have found gypsum on Mars through this spectral signature using an imaging spectrometer called the on the Mars Reconnaissance Orbiter called CRISM. And the rover has an imaging or a spectrometer on it too, not quite an imaging one. So next. So we know here on Earth, wherever there's water, doesn't matter how hot or cold, as long as it's liquid water, how salty it is, what the pH is, how radioactive it is. If there's water there, there's life that's figured out a way to make its living in that water. So that's exciting to us when we find minerals that could only be made by large amounts of water that have been hanging around for long periods of time. So this is a pretty bland spectrum. Good grief, what is that? Oh, it must be the white stuff, baking soda. And this is our favorite, sodium chloride. And in fact, those two dips for sodium chloride, which is the purple line, salt, they're influenced by the humidity and how much water and makes some playas that are very salty not as useful as others. But they actually make humidity detectors out of certain salts. And these spectral features are one way that they can use them as transducers. So that's how spectral fingerprints can be used to identify the chemistry of materials. All right. So I've mentioned the powerful greenhouse gas of water vapor. Let me ask Andrew, who's been so kind to help me with these demos, to speak to these next few slides.
Great. So as that last demo demonstrated, different terrestrial land cover types, or surfaces, have their own unique spectral signatures, but also trace gases in the atmosphere also have absorption features that we can see with our instruments. So really my focus of my work here at JPL is to develop techniques to identify and map greenhouse gas emissions. And we can do that with various instruments. We can do it with orbital satellite instruments that are designed exclusively for this work. And we can also use some of the airborne instruments that we discussed today, the AVIRIS Classic and AVIRIS Next Gen instrument. And what I've plotted here are the atmospheric absorption features for methane in the upper panel. And we can see that over the entire wavelength range of our instrument, there are various portions of the electromagnetic spectrum in which there are absorption features. The most strong absorption features are centered somewhere between 2250 and 2450 nanometers, as shown in the bright red curve there. And so it's those absorption features that we can actually use to quantify methane within those AVIRIS and AVIRIS Next Gen scenes. For carbon dioxide, we have 3 very strong absorption features that are at a shorter wavelength, around 2000 nanometers, and you can see that very clearly in bright green. So as part of multiple campaigns that we do here at JPL, we do fly our airborne instruments to try to identify emissions of both methane and carbon dioxide. This is a survey that we did a few years ago in the Four Corners area in the United States. We took the AVIRIS Next Gen instrument and we flew over 2,500 square kilometers over a few days. And each of these push pins indicates a location where we were able to map methane emissions from a source. How do we actually do that in the aircraft? Well, we have this real-time detection capability that a colleague of mine, David Thompson, really pioneered. And this is another colleague in our group, Ryan Pavlik, supporting a recent campaign that we did where we fly over regions looking for methane emissions. So he's in the aircraft here looking at a computer monitor, and on the monitor we've got the data that's being piped in from the instrument that's looking down at the ground. So you can see on the right-hand side sort of the red, green, and blue bands of what we would see with our eyes. And what we've overlaid are methane plumes in red, and you really can't see that in this example. But what this allows us to do is to fly over large areas to look for methane plumes. We can then flag them on the aircraft and communicate that information down to the ground for follow-up. So what do these plumes actually look like? Well, this is one example of the 250 plumes that we observed at Four Corners. You can see that the pixel resolution for the plume it's a little bit coarse. So each image pixel of the AVIRIS Next Gen instrument in this example, I think, is somewhere between 3 and 5 meters per pixel. And we've overlaid it on Google Earth, which has improved spatial resolution. So you can actually resolve that individual well pad, and that helps us with interpretation. So what you can see from this example is the red, the higher red values, the more intense red values are higher methane concentrations. And you can sort of interpret this and try to determine where the plume is coming from. It's pretty clear that it's sort of from the northern portion of this well pad as the emission source. What I had mentioned before is we have this real-time capability. So if we identify this in the plane, folks can communicate it down to the ground for follow-up. And we do that with a thermal camera, which is shown here on a tripod. And this is a picture, I think, that Mark took of our colleagues Scott Nolte as part of the Four Corners campaign. So we were driving around trying to verify some of the observed plumes with the AVIRIS Next Gen instrument using this thermal camera. The thermal camera is sensitive at about 7 microns for methane absorption features, and it allows us to take videos of methane plumes. You may have seen some of these types of examples from other examples for other methane leaks in the area. So this is the example of the video that we acquired for that methane plume that we saw with the IRIS NextGen instrument. So this is actually coming from a tank that's buried partially. And if we were to look at this with our bare eyes, you would see nothing, right? Maybe you would smell something if there was some type of additive added. But this is a great example of us verifying an observation that we did with our aircraft. Here's another example of a methane plume that doesn't appear to be associated with any visible infrastructure in the scene. We kind of have a well pad in the southern portion of the scene, but it appears to be sort of emanating from around those dirt roads. You can see that there's one pixel that is the brightest red, and that's the highest concentration. So that is the location that we would target if we wanted to try to verify if there was actually methane being emitted at that location. And for this example, we also set up the thermal camera to look off of the dirt road to try to verify the methane plume that we saw with the IRIS NextGen instrument. And you can see that we have a dead tree in the left-hand portion of the scene. What's interesting is that plants can be killed by excess levels of methane in the roots. So that was made it even more intriguing for us to spend a little bit of time to try to find this emission source. What was even more telling was the fact that there was actually a few yellow flags placed in a line, and they had a 1-800 number of the local gas company. So this was in fact a buried natural gas pipeline in an area of natural gas extraction. So we spent some time to try to look for the plume using a thermal camera, and we did in fact see methane. I apologize for the quality of this video. It's pretty poor, but you can see clearly we've got methane coming out of the ground. So this was a buried natural gas pipeline where concentrations were coming up through the ground at high enough values that we could see that with our aircraft. As part of this work, we're developing quantitative gas retrievals. So that means that for every image pixel that has a color here, we're able to estimate how much methane is in that pixel above background. And you can see our units are in methane enhancements in parts per million meters. And that's in excess of 8,000 ppm for the highest concentrations. And the way that we do these retrievals is we take a measured radiance. So for every image pixel in this scene, AVIRIS measures a radiance, and we focus in a portion of the shortwave infrared spectrum from 2,200 to 2,400 nanometers, and we take our measured radiance, which is black, and we match it to a modeled radiance as shown in red here with a known elevated concentration of gas. So when they are best fit, we can estimate how much gas is present in that pixel. So we do that for the entire scene, and we can map out the plume quantitatively. We're also looking at other emission sources, not only oil and gas related. So this is an example of a methane plume coming off of a landfill in Southern California. It's clearly at least one plume, maybe two plumes. And we've used purple and pink for the color scheme here. And we also collaborated with some German researchers at the University of Bremen who have a MAMAP instrument. This is an instrument that's related but has non-imaging capabilities. So they fly back and forth over the landfill and have measurements at each of those points that are visible. So the red points have higher methane than the green ones. And you can see there is pretty good agreement between what we saw with the IRIS NextGen instrument and what MAMAP saw, even though they weren't flown exactly at the same time. We're also working on carbon dioxide related retrievals. Similar process, we're using a different wavelength range from 1900 to 2100 nanometers. Same idea, you match your measured and modeled radiances. And with that, I think we're going to go ahead and have a CO2 demo to kind of illustrate this capability.
Did you say CO2? You can get your CO2 right here. So we're going to use this spectrometer, portable, non-imaging spectrometer. We're going to use this integrating sphere as a white cavity, and we have a light bulb here. Now I'm using an incandescent, well, first, Andrew, put it in raw mode.
Raw mode? I was going to change the axes first.
No, just...
I'll let you take over.
Sure, go to, sorry, I'm changing up on poor Andrew here because I didn't go over this part. So first we're going to turn on a red LED. Come on, don't make a liar out of me. What's going on? Then we're going to turn on a green LED. Where'd it go?
To change the scale?
Yeah.
Yeah.
All right.
So we're at
No,
0 to
hang on.
1.1, so
Let me
you
go,
wanted 0 to...
Let me optimize. There we go. And then the scale will have to change to, well, let's just see what the scale's going to have to change at. There we go. So let's change the scale to axes 0 to 200 maybe. Oh, well, we've got more signal than that there. So yeah, this is what scientists like, you know. All right. Do I have 100 or 1,000?
100.
Oh, you young eyes. All right. Can you make that 1,000?
Yeah.
All right. So maybe go to 5,000. All right. Bump. Good. Bump at 600 and almost 700 nanometers. And I can turn the bump up and down with this knob here. And then here we have another bump at 550 nanometers. That's the green one. Okay. And then we have another bump at about 400 nanometers. Here's all three of them put together. 3 bumps, 3 light sources. But the radiation that the part of the electromagnetic spectrum that we want to use to measure methane is way out at 2,000. These LEDs aren't putting out any light at 2,000, so I want to put a light bulb in there, an incandescent source that puts out energy at 2,000. That was the whole point of that. So do an optimization.
You want me to change the scales too, right?
And then we'll do a right reference, and then we'll change the scale. I've carried this thing, or things like it, on my back around the world. It was a JPLer that originally developed this portable technology, and I've been a beta tester for decades. So I'm not being hard on Andrew, it's just I know these things.
All right, so we white reference and then change the scale, correct?
Correct. So what, 0.8, 1.1 to 0.8. All right, so everything's stable. Dividing the same thing by the same thing. We've taken our white reference. So what we're going to do is we're going to add, see, an experiment adds one thing so that you're sure you're measuring the one thing. And in fact, a good scientific paper goes into excruciating detail. Not only this is what I measured, but this is how I measured it, and this is how I know I did it right. And a really good paper says, and this is how you might even improve on the measurement. So I'm going to do something, we'll take another white reference. The light bulb changes slightly in temperature with time, and so you get that little dip in the blue. So this is acetic acid, white vinegar. This is sodium bicarbonate, baking soda. You put them together, they make carbon dioxide. I've put it in a bolus here so this slows the reaction down a little bit. Our colleague Morgan Cable, who's an exochemist, taught us about that one. Otherwise, if you just dump a bunch of baking soda in there, you get a big mess, right? So what's happening now is we've got bubbling going on, and ostensibly we have CO2 coming out of this thing. And CO2 is a little heavier, just a little heavier than air. And we're going to just kind of hold it there. Don't stick it all the way in. There you go. And with time, as the sphere fills up with CO2, we should start seeing a spectral feature at around 2 microns, 2,000 nanometers, build up. Now I'm kind of cheating here. This is a white chamber, which means that the light from the bulb bounces around and goes through a whole lot of CO2 and picks up the spectral signature of the CO2 before it makes it into the Gazinta end. But this is a demonstration of the mechanism of the process by which we measure atmospheric carbon dioxide.
And this is directly analogous to what we do with the airborne instrument. So it's those 3 absorption features that are growing and growing that we're mapping and how we do our quantitative gas retrievals per pixel basis.
Okay,
The
Andrew,
same concept.
we're getting some plastic tubing spectra
yeah?
in there too. This is the one thing about an integrating sphere, it mushes up everything and anything that gets next to it or in it. So we can do the circularity skeptical proof by emptying out the sphere. And one way to do that is to blow in it. There we go, and it goes away. But what also comes in, if I breathe slowly. So besides bad breath, what gas do you think is responsible for those extra? Yes, water vapor. Very powerful greenhouse gas. So that's how it works. I think we've covered all of the points we were going to cover. Okay. Yes, indeed we have. Good. Thank you. So next is a bunch of videos. These next videos and slides tell the story of what it has been like to work with the Avarice airborne spectrometer. Let's go for a ride on a research aircraft that's carrying the Avarice next generation imaging spectrometer. This is let me back up. Let's see it again. This is a de Havilland Canada DHC-6 Twin Otter taking off from Bob Hope Airport, California. This is my favorite part, takeoff, besides a good landing. Here we are departing Ponca City, Oklahoma. These planes were modified for tourism with the installation of large windows. I'm taking the video from a special bubble window looking forward. You can see the cockpit door handle sticking out from the skin of the airplane on the right. And it's pretty flat out there in Ponca City, Oklahoma. So here we are in flight, hi Mom, over Four Corners, New Mexico with the Avarice Next Generation instrument, collecting some of the data that Andrew just showed. This is my colleague David Thompson, the guy who was developing the real-time analysis algorithm. That display showed we're flying at about 16,000 feet. That's our real-time display, and I'll explain that more about that later. But here you see the layout of the aircraft, right? What it looks like behind the instrument is in front of that fan. That white fan, by the way, is used to keep the plane cool in the hot sun when we're not moving through the air. There's a green tank there with oxygen in it, and that's why we have those cannula in our noses, because we're actually 16,000 feet. And then if you look out the window, those aren't anthills down there. Those are all natural gas extraction pads. And that's how it's done in Four Corners, New Mexico. And there's more data, and you can see a little bit of red on the display there on to the right. That's the real-time extraction display. Bye, David. Okay, did I mention there's a big hole in the bottom of the airplane for the instruments to look out of? That's why we wear oxygen, because you can't pressurize the plane. And no, the instrument isn't moving, the airplane is moving. It's on a stabilization mount to keep things nice and straight. And we're in flight over the Four Corners area in New Mexico. Another favorite thing while flying, a good landing. So here we are landing in Ponca City. And let me go back again. Note the hole in the bottom of the airplane, and we can see the ground through the hole, right? And this is with the CFIS spectral mapping instrument looking out that hole. And the chlorophyll fluorescence imaging spectrometer directly measures chlorophyll in action as it uses the energy of sunlight to make food from air and water. It's a very exciting, brand new measurement that we're developing. The moment of touchdown, a good pilot, nice and smooth. can always tell the difference between a Navy-trained pilot and an Army-trained pilot, if you've ever flown commercially. In the Navy, they learn how to catch the tail hook, right? How to catch that trap wire, and so they put it down, boom. Whereas the Army and the Air Force boys, they use the whole runway to land. So here we are over Zion National Park in Utah. And this is the visitor center below. This is during one of those transit flights, my favorite transit flight from Southern California to central Colorado, where the facility is where they maintain these airplanes. Ooh, can I go? Ooh, ooh. Yeah, those big windows are really something. Now this is what we're looking at in the plane during data acquisition. This is our live readout for instrument operators. And over here on the left is what we call a waterfall display. And it shows us what we've just flown over. And in this case, our target is that little square there with all the little individual plots of different species of plants. And then over on the right is our real-time focal plane array display, indiscernible to the normal human eye. If you happen to build these things and calibrate them, you can actually interpret what they have to say. That's a whole story just explaining what that is. But it helps, gives us a warm, fuzzy feeling when it looks right while we're operating the plane. Here's head honcho Michael Eastwood and primary investigator Robert Green of the AVRIS program, sending AVRIS Next Generation off from our loading dock at JPL to India. We got to travel to India. Here we are the first day after arriving and recuperating from jet lag in Hyderabad, India. And Sven here and I were waiting for our van from the airfield gate back to the hotel after installing the instrument in the plane. And the call of the muezzin to prayer started just as I turned on the camera. And India is definitely a multicultural place. I highly recommend visiting. My wife loved it. But watch what you eat. So here we are in Mangalore, over Mangalore. And you can see here's Andrew inside the plane on the ground before we took off. And Ernesto over on the right, about to take off on yet another mission. And this is a freighter leaving the port of Mangaluru on the southwest coast of India. And we did make the local papers. Here we are in Bhubaneswar, which is over on the eastern side of southern India. And that's Sven, again, in front of the Indian aircraft, King Air aircraft that we used. Yeah, that actually, the reason why we used that particular aircraft is they were using it for photographic mapping, right? They had a system made by Kodak looking out a hole in the bottom of the plane that was just big enough for us to look out of. And we knew that, and we found the same model plane with the same hole cut in it, same size hole cut in it in the States, and we fitted everything to that, and then we took it all apart and took it to India. It was cheaper to do that than it was to fly the plane from the States to India. And another airplane we use is the ER-2 high-altitude aircraft, research craft. NASA has two of them. They're old U-2 spy planes that have been converted for scientific use. And this photo was taken from the ground. Old ER-2 pilots that were U-2 trained back in the day kind of would look on these pictures with chagrin because you're not supposed to know where they are. They're a spy plane, right? But if you're the scientist that said, I want you to fly over this spot at this particular time and it better be a clear day, then you know when to point your camera straight up and take a picture. And that's how we were able to get some of these pictures. And this was taken by a researcher at Kilauea Lava Lake of the ER-2. And on the ER-2 was this instrument here that we're filling with liquid nitrogen, AVRIS Classic. Some of the technology we use requires low temperatures to operate properly. And then here's the ER-2 taking off from the Palmdale Airport, just north of Los Angeles. It's got these pogos in the wings because they're so long, when they're full of fuel, they would drag on the ground. And as it takes off, those pogos will fall out, one then the other. That's why we're chasing the plane, to make sure we can pick them up. And then the pilot pulls the stick back and shoots up to 65,000 feet faster than any other plane. Just goes. Now this plane actually surfs pressure waves at the upper part of the stratosphere. The engine is at full out. at that altitude, and at that pressure, it has 18% of the thrust that it does down on the ground, to give you an idea of how thin the air is. So, and there's a link on the last slide to give a much better report of ER2 operations during our Hawaiian campaign. So here we are looking through the targeting periscope that the pilot sees, and this is looking at Hawaii Volcanoes National Park. And the plume on the right-hand side of that crater is from Halemaumau crater on the right side of Kilauea crater, the larger crater. Note the altimeter down here says 64,550. And this photo is by ER2 pilot Stu Brochet. And it's so cool to work with a team, and you get a photo like this in your email box like right after he lands. It's like, oh, look what I did today. It's so cool, right? And it really validates your contribution to the overall effort. And this is another picture that he took and sent after he landed. He's so high he can actually, he's right at the boundary of the atmosphere. So the sky's not blue above him, it's black. There's no air there. Way too cool. So here's some links to websites with more information about imaging spectroscopy at JPL. And many of you probably know that this image was taken by astronaut William Anders with a chemical film camera aboard Apollo 8 in 1968. With the lifeless craters of the moon in the foreground, this photograph shows our finite Earth, where all of human history has happened, against the cold nothingness of space. It has become an icon of planetary environmental awareness. And it reminds us of how, by exploring other planets, we learn so much about our own. Personally, it is fascinating to work with people who have a planetary perspective. I've been standing out in the field in the middle of nowhere with a researcher when they point to the strata in a nearby hill and rattle off a billion-year story of terrestrial geology, cosmic events, and planetary evolution that connects in a deep context to the purpose of the campaign that brought us together. My purpose this evening has been to share with you my own fascination of the science in action that I've been exposed to, and to illuminate through lecture and demonstration a few key points. JPL studies planets, including the most important planet in our universe, our Earth. Imaging spectroscopy is a powerful tool for studying planets. Imaging spectroscopy is a scientific remote sensing tool. And remote sensing is something that NASA does best. And I've had another goal, to leave you with an appreciation of the philosophy and process of the best survival tool ever created, science. Thank you for your attention. Andrew and I would be very pleased to entertain questions, but if you have a question, please step up to the microphone so everybody online and out there and the rest of the world behind these camera lenses can hear your question. We'll come down. Step right on up, don't be shy. Don't be shy, I'm going to make you stand.
Hello.
Hi.
Thank you, Mark and Andrew. That was really cool. I was wondering, how many Avarice rigs do you guys have, and what's the current status of Avarice research?
Well, Avarice rigs?
Or
Instruments.
instruments, yeah.
Right, yeah, kits. Well, right now there's a team flying the PRISM imaging spectrometer out to Hawaii, and they're going to be flying for the next several weeks over Hawaii, Guam, and Palau. Avarice Next Generation just finished a stint on the ER2 over the Southwest. Avarice Classic is on its way to Georgia. It's going to be flying to help calibrate the GOES-R geosynchronous weather satellite. I calibrate the Avarice instruments, and so they're using my Calibrate to calibrate their satellite. It's really neat. Anyway.
And there is actually some related instruments that we built at JPL that are now deployed to other organizations. So there's a group at Stanford that has an instrument that they fly. There's also
That's the Carnegie Airborne Observatory, CAO. They have their own website. It's fascinating because they have a LiDAR mounted with it, and they're able to map jungles and forests, and they've got these really cool videos, and I highly recommend it. Carnegie Airborne Observatory, that's an NGO, basically.
And then there's a NEON program as well, which has multiple spectrometers that were built by JPL that is also flying to do the similar types of work. But
NEON is the National Ecological Observatory Network. They have the mandate to measure for the next 30 years changes to 50 representative environmental types in North America and their response to climate change. A very interesting website as well, and they have a very active airborne program. And we've made spectrometers for other government agencies. And that's about all I can say about that.
And we're always looking to make new spectrometers for new applications.
Make them smaller, lighter, more efficient, better signal-to-noise ratio, better, and it's great. But JPL isn't in the business of mass producing things. We're in the business of researching things and how to do it better.
Thank you.
Yes, sir.
In your section about tracking methane plumes over like oil wells, and who requests those measurements, and what happens to the data after you collect it? Like, do you report it somewhere, or does a repair team come out and fix the leak, or?
Yeah, that's a great question. So we have multiple flight campaigns. I think I'll talk mostly about the one we did at Four Corners, but that was a NASA-funded project, science-based, to really focus on demonstrating capabilities. So we had really never demonstrated the real-time capability before, and we targeted that region because we knew that we'd have a good level of success in identifying those plumes. So that was funded for scientific research. In the examples where we did find interesting plumes, we did communicate those to, as I stated, to local operators on the ground. So for those natural gas pipeline
Mostly as a courtesy, right? They actually came out to fix one of the things we found.
Yep. So in that context, we view it as a kind of a win for everyone. It's a win for the environment because it's less methane in the atmosphere for the oil and gas company, or for the pipeline operator, that's lost product that if they know about, they can do something about, so they're not losing money. We're also working with other agencies, it's a good point to bring up. So we do have a data sharing policy where we do have to make data available to users, including the data that we measure with our instruments, and we do that routinely on our websites that are publicly available.
NASA is a publicly funded agency. All of the data we collect is publicly available. You may need to have your own supercomputer to look at it, but it's publicly available.
Cool, thank you.
Oh, we have questions from the web, the connecting network of pipes and tubes, right? So Z. Mihaly asks, Mark, what is your favorite part of spectroscopy? The blue part. I was being literal, but seriously, blue light is very difficult and very challenging to deal with and to calibrate with, because the incandescent sources we use in the laboratory are blue bereft. They just don't put out nearly as much blue light as they do everything else. But I think Z. Mihaly means this question in perhaps a little more generic. Spectroscopy has taken me to the corners of the earth. It's helped me meet people I would have never had an opportunity to talk to and learn from otherwise, to cast my gaze upon the northern lights and the Southern Star, or the Southern Cross, and to interact with scientific colleagues who come from wildly different cultures and have different perspectives on life, but we share this one thing, science in common. And being able to talk the language of science has enabled me to just form that bridge with that real connection with people on a very deep level. So and in short, the travel and the situations. Yes, I have one more question, but I will take yours first.
Are there other applications like the radar mapping with imaging. It's a different, different wavelength.
Different part of the spectrum, don't know anything about it.
Yes, yeah, different spectrum. And I mean, if you combine, I'm sure that it has been done before, you combine the radar mapping, like,
Yes,
for
that's
example,
actually a very powerful way to
yeah,
do remote
like
sensing, is
the
to combine.
Google mapping started with the radar mapping.
Well,
right?
yeah, you can layer up the
and
data.
then,
Yep.
You have the Magellan, the Venus radar mapping, okay?
Yep. You
And
saw through the clouds that way.
how do you do, or how would it done that you get the visual and onto the radar mapping?
Well, it's called
Do you have a-
georeferencing.
Yeah, how do you do it?
Well, you can do it by recognizing points that you know where they are. That's one way to do it. And the other way to do it is to know the geometry of observation very, very well. It's kind of like the idea of what's called photogrammetry. You know where your camera's pointing, and you know where every part of the film projects through the lens and then hits on the ground. So when I say pixels, it's a digital way of thinking of imagery. We're not actually projecting squares like these tiles on the floor on the ground. It's really just a bunch of blurry spots that happen to be representable in a pattern like a checkerboard. But for precision photogrammetry and precision georeferencing, we know the latitude and longitude of each corner of each one of those imaginary squares that's projected on the ground as if we were shining a light from the instrument to the ground. And if you know the latitude and longitudes of those four corners, you know the area that you've averaged your measurement over. And then if you happen to fly over again, you know how the other pixels line up with that, and you can do what's called change detection, which is a very sensitive thing to do. But it's that precision registration of your instrument's geometric characteristics, how the image is warped, where everything actually hits the ground. And that goes into a big electronic file in a way that it's associated with each pixel. And there's specific, like JPEG or TIFF, or, well, there's something else called a mental block right now, but it's a file type that has all of that information, not only the wavelength, but where it was looking on the Earth. And so that's how you line up all of those different layers of data for interpretation. But that interpretation sometimes is more than just looking at it and recognizing something with your eye, because the universe is not a human thing, right? And so it's not always recognizable easily to a human being what's going on. And so we program computers with the laws of physics to try and understand and interpret these things. And imagery is one of the ways we've evolved to understand data, and that's how it's displayed. But that's not necessarily the most powerful way there is to look at it.
And I guess
If that answers the
just to
question.
follow up, there are airborne radar systems that more and more folks are using. We have satellite radar systems, we have airborne radar systems. We mentioned the LiDAR system, which is an active laser pulse that's also used. And what we like to do is wherever we can, we try to do sensor fusion. You bring data products and measurements together so you can answer questions that you couldn't necessarily answer only with radar, only with Avarice Next Gen, only with LiDAR. So that's why we're trying to bring things together.
Right, I've concentrated on reflected sunlight, but there are other ways to do it. Reflected sunlight is passive remote sensing. There's active remote sensing. So instead of taking a picture using the ambient light in the room, take a flashlight along with you. That's active remote sensing, right? So that could be radar, that can be a laser, LiDAR. You can also do remote sensing in the thermal part of the spectrum, and all these layers and the physical understanding of where that radiation being something that emits from a point and goes to another point in a straight line, radiates, right? Understanding the physics of all that and the phenomenology of it, because when you're doing remote sensing, you're not measuring your quantity directly, you're measuring some indirect effect. In the case of reflected sunlight, how the spectral fingerprint is manifested. But from that indirect effect, you're making an estimate. So that's a general view of remote sensing 101. Mm-hmm. So I have another question, and I would encourage anybody else to step up to the microphone. Step on up to the microphone. Clayton asks on the internet, could we use the spectrum of light from an exoplanet to detect organic matter? Boy, you just asked the right people. Or would the atmosphere block it out? Not necessarily. It kind of depends on the atmosphere. And that's called atmospheric correction. And if you know what the atmosphere is, you can correct for that. But there may be an exomoon that doesn't have much of an atmosphere that might have evidence of life leaking out of the cracks in the ice. Europa, we know it's blue ice with this reddish material coming out of the cracks. Well, we sure would like to get some spectral detection, and there's a mission that Andrew and I are involved with, that MICE, that is proposed to go to Europa and make those measurements to figure out what that red stuff is and if it's organic material. But an exoplanet, would the atmosphere block it out? No, there are clear windows in the atmosphere. Atmospheres are complex and compound things with many spectra all put together and teasing those spectra apart. But some of the spectra, like the spectrum of water vapor, are so distinct you just can't miss it. And that's one of the things we would look for in an exoplanet's atmosphere. Okay, we're all hungry, want to go home. Thank you.
Great, thanks.